What specific problem does dynamic fine-tuning, DFT, aim to solve regarding supervised fine-tuning, SFT, and how does it address the limitations of SFT?
Dynamic fine-tuning, DFT, aims to solve the problem of the ill-posed reward structure inherent in supervised fine-tuning, SFT, which leads to unbounded variance in gradient updates and poor generalization. The mathematical analysis reveals that SFT's gradient can be viewed as a policy gradient method, with an implicit reward that is sparse and inversely proportional to the model's probability of expert actions. DFT addresses these limitations by dynamically reweighting the SFT objectives based on token probabilities, effectively neutralizing the inverse probability weighting that causes instability. This transformation results in a stable, uniformly weighted update procedure, which enhances the model's ability to generalize across diverse tasks. Empirical results demonstrate that DFT significantly outperforms standard SFT, particularly on challenging datasets, highlighting its robustness and improved performance.
How does the proposed method, DFT, work? Please illustrate the step-by-step process of the algorithm, detailing the mathematical transformations applied during fine-tuning.
The proposed method, dynamic fine-tuning, DFT, works by addressing the ill-posed reward structure inherent in supervised fine-tuning, SFT. First, DFT begins with the standard SFT objective, which minimizes the sentence-level cross-entropy loss based on expert demonstrations. The key transformation occurs when the SFT gradient is interpreted as a policy gradient with an implicit reward structure, where the reward is sparse and inversely proportional to the model's probability of expert actions. To rectify this, DFT rescales the SFT loss by dynamically reweighting the reward using the model's token probabilities, effectively neutralizing the inverse probability weighting that leads to high variance in gradient estimates. This results in a modified gradient that is stable and uniformly weighted, allowing for more effective learning and improved generalization across various tasks and models.
Can you provide a simple yet illustrative example of how DFT operates in practical scenarios? Walk through the main steps of the algorithm using a hypothetical expert demonstration scenario.
Dynamic fine-tuning, DFT, operates by addressing the limitations of supervised fine-tuning, SFT, through a specific reweighting mechanism. For instance, consider a hypothetical expert demonstration where the expert provides a solution to a math problem, and the model's task is to replicate this solution. In the DFT process, the model first calculates the standard SFT loss based on the expert's response. However, instead of using this loss directly, DFT rescales it by the probability of the model's predicted token, effectively neutralizing the inverse probability weighting that can lead to high variance in gradient updates. This means that if the model assigns a low probability to the expert's action, the loss is adjusted to prevent overemphasis on rare exact matches, resulting in a more stable and uniform gradient update. Consequently, DFT allows the model to learn more effectively from the expert demonstration, improving generalization and performance across various tasks, as evidenced by significant gains in accuracy on challenging benchmarks compared to standard SFT.
What are the theoretical benefits of using DFT over traditional SFT, particularly in terms of gradient variance and generalization capabilities?
Theoretical benefits of using dynamic fine-tuning, DFT, over traditional supervised fine-tuning, SFT, include a significant reduction in gradient variance and improved generalization capabilities. DFT addresses the ill-posed reward structure inherent in SFT by dynamically rescaling the standard SFT objectives with a token probability, which neutralizes the inverse probability weighting that leads to unbounded variance in the gradient updates. This transformation results in a stable, uniformly weighted update procedure, contrasting with SFT's unstable and biased mechanism that suffers from high variance when the model assigns low probabilities to expert actions. Empirical results demonstrate that DFT consistently outperforms SFT, particularly on challenging datasets where SFT tends to overfit, thereby highlighting DFT's robustness and superior generalization across various tasks and model architectures. Overall, DFT's approach not only stabilizes the optimization landscape, but also enhances the model's ability to generalize beyond the training data, making it a more effective fine-tuning strategy.
How has the effectiveness of DFT been validated in the paper? Discuss the datasets, benchmarks, and metrics that were used to assess its performance compared to SFT and other methods.
The effectiveness of dynamic fine-tuning, DFT, has been validated through extensive experiments on various datasets and benchmarks, particularly focusing on mathematical reasoning tasks. The primary dataset used for training was the Numinimath COT dataset, which includes around 860,000 mathematical problems, with experiments conducted on a sampled subset of 100,000 instances. DFT was evaluated against established benchmarks such as Math 500, Minerva Math, Olympiad Bench, AMY 2024, and AMC 2023, where it consistently demonstrated significant performance improvements over standard supervised fine-tuning, SFT. For instance, DFT achieved an average gain of +1.5, 66 points over the Quen 2.5 Math 1, 5B baseline, which was over 5.9 times greater than the +2.09 point improvement from SFT. Additionally, DFT outperformed both offline and online reinforcement learning methods, such as RFT and GRPO, indicating its robustness and superior generalization capabilities across diverse tasks and model architectures.
What key findings regarding performance improvements and limitations of DFT were reported in the results section? Specifically, how did DFT perform across different model architectures and datasets?
The results section highlights that dynamic fine-tuning, DFT, consistently outperformed standard supervised fine-tuning, SFT, across various model architectures and datasets. For instance, DFT achieved an average gain of +1.5, 66 points over the Quen 2.5 Math 1, 5B baseline, significantly exceeding SF's +2.09 point improvement. This trend was observed across other models as well, with DFT yielding higher gains than SFT for LLAMA3, 2-3B, +3.46 versus +2.05, Llama-3.1-8B, +10.02 versus +5.33, and DEPSEKMATH7B, +15.51 versus +7.18. Notably, DFT demonstrated robust generalization capabilities, particularly on challenging benchmarks like Olympiad Bench and AMY 2024, where SFT experienced performance degradation. Overall, DFT not only scaled effectively across different model sizes, but also exhibited greater resilience in difficult reasoning tasks, underscoring its potential as a more effective fine-tuning strategy.